and you really struggled with writing the actual formulas down, make sure you review it. This is really going to be important. Balancing equations. I'm putting stars next to all of them because they're all very important. You need to be able to properly balance your equations. So that example that I did, if I'd had it not properly balanced, I wouldn't have known how many moles to transfer over. Determining molar mass, also really, really important. And you guys saw that I did that with the soap and the sodium hydroxide. So that's from like unit 3 or 4 as well, I think. Calculating moles to mass. So going between all of your conversions. And milliliters to moles. So all of those different conversions, those multiple conversions, you guys need to be able to know how to do at this point. Yeah, so all of them we are going to apply in this unit. So make sure that you're comfortable with those things. If you're not comfortable with them, study up, ask me questions. We need to make sure that you're in a place where you can comfortably do those to get through this unit. Okay. So making soap and baking brownies are both applied chemistry. And we're going to be looking at a lot of applied chemistry in this unit where we're actually taking a, it says receipt, sorry, that should say recipe. Where we're actually taking stuff and figuring out how many ingredients or reactants we need. So the recipe is kind of like a balanced chemical equation. It tells you the ratio of things that you need to produce a certain amount of product. Okay, so we're going to think about a recipe for brownies that makes 24 brownies. So 24 brownies is going to be our product in this metaphor for a chemical reaction. You'd have a detailed list of each quantity of ingredients used to produce those 24 brownies. Recipe is proportional. Oh, whoops. Sorry. The recipe, the reactants, shows the ratios of the various ingredients in that recipe. And the recipe is proportional. So basically, when you're baking, you don't want to put too many eggs in, like a high proportion of eggs that then you end up with these like runny mess of a thing that doesn't bake properly, right? So the proportions are really important in brownie baking and in chemistry. So if you want 48 brownies, you're going to double everything, right? So it's all about proportions. And if you want 12, you're going to cut it in half. I almost said 10, 12. Should say recipes. Okay, recipes are based on observations. As well as trial and error. Have any of you tried to bake something not using a recipe and just like gone totally off script before? Oh yeah? Did it work out? Sort of? Okay. That's good. Did you like try it again afterwards and try to improve it? Oh, okay. Yeah, so a lot of the time, like if you make something and you don't like it or you feel like there's room for improvement, you're just gonna try it again. And maybe make more mistakes, and eventually you're going to refine the proportions. So that's basing this on observations, like I added too many eggs, so it's too runny or whatever, or I guess water would do that, not eggs. I'm not a baker, you guys. But yeah, trial and error. You're going to just try to correct whatever you did based on your observation. And then if you make another mistake, you're going to try to correct that. So recipes are just based on trying stuff. You can write any recipe, but that doesn't necessarily mean you get the desired food. If the proportions are off, it's not going to end up being good. So if the proportions are not correct, the product might be more like rocks than like brownies. So therefore, if the proportions are correct, are not correct, the product may not be what you want. So that's like with the soap. Somebody asked, well, do we need to know about the water and the olive oil as well as the sodium hydroxide? Yeah, you absolutely do. So we need to know the proportions of all of our reactants so that our product is what we want. Okay, so a chemical reaction equation is like a recipe. It shows the ratios among the reactants and the products. So this is where our coefficients get really important. And what we're actually seeing in these coefficients is molar ratios. So 2 atoms, this formula is 2 atoms of magnesium plus 1 molecule of oxygen gas make 2 molecules of magnesium oxide. And you can increase these. You can double that. 4 atoms of magnesium and 2 molecules of oxygen is going to make 4 molecules of magnesium oxide. You can multiply that by 1,000. You can increase this in whatever increment you want. It's the ratio stays the same. So having a chemical reaction that's balanced allows us to predict products and figure out how much reactant we need because the ratio stays the same the whole time. Okay, page. So again, cooking is really similar to chemistry. Creativity is desirable, but attention to detail is also very important. Have any of you watched The Great Canadian Baker or any of those shows? Yeah, there's some pretty entertaining ones where people make like horrendous mistakes because of their lack of attention to detail. Anyway, so it's just very important, baking and chemistry. Neither activity allows exact measurements, but really precise and as accurate as you can go are necessary. Both of them use experimental results. To develop recipes that can be used to predict the product of reactions. Okay, so this word, we are going to say it a lot, stoichiometry. Okay, can everybody just try saying stoichiometry aloud? Let's do it, stoichiometry. 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 It's a weird one. Phonetically, it looks like it would be like stoichiometry or something. But it's kind of like this is a K. Yeah, stoichiometry. It's the relationship between the amount of reactants used to the amount of products produced during a chemical reaction. And the coefficients is what's giving us that ratio. Give us the ratio of molecules and the moles of the substances in the reaction. It is really important that we convert to moles when we're using stoichiometry, because just like we were doing in, it was a couple chapters ago. Basically, when we're comparing between things, we need to be in moles, because some things have more mass than others per gram and everything. So it's going to be really important that we're always pretty much going back to moles. Okay, so an example of something that we might see here, 2 hydrogens plus 1 oxygen makes 2 water molecules. So if you take hydrogen gas and mix it with oxygen gas, you're going to get some water. So that means 2 molecules of hydrogen, 1 molecule of O2 goes to 2 molecules of H2O. And you can take that ratio and you can turn it into moles directly. As soon as you've got it in molecules, you can go directly to moles for the ratio. So the ratio of molecules is equal to the ratio of moles. So does anybody know what NH3 is? Yeah. Ammonia, yeah, awesome. And this is also fertilizer. So this is what we might use in our gardens as fertilizer. So how many molecules of N2 are required to react with 15 molecules of H2? So what we can do is we can solve this using unitary rates. So that's the coefficients of the balanced equation, and that gives you the unitary rates relating molecules of another one substance. Sorry, I didn't leave much room here. Molecules of one substance to molecules of another. So for example, in this combination, going from N2 and H2 to NH3 to ammonia, what we end up seeing is we want to know how many molecules of nitrogen is needed to react with 15 molecules of hydrogen gas. So what we can do is go 15, so this is from our math for chemistry unit, 15 molecules of H2, and then we're going to multiply that by our unitary rate, which is, in the balanced equation, 3 to 1. So 1 molecule of N2 for every 3 molecules of H2. And then when we do that, we do 15 divided by 3, and we end up needing 5 molecules of N2. So if we want to make 2 ammonia, we need 15 hydrogen molecules and 15 hydrogen molecules and 5 nitrogen molecules. Yeah. Oh, the question. Yeah. Well, no, it was a good question because other people might have been thinking that. He's like, where'd you get that 15 from? Are you just making up numbers? Okay. All right, so another example here. How many moles of oxygen are required to react with with magnesium to produce 1 mole of magnesium oxide? So what we're going to do is we are going to write the reaction equation first, and we're going to balance it. All right, let's go. So magnesium, oxygen, magnesium oxide, which is just MgO. If we balance that, we're going to need to throw a 2 there and a 2 there. Okay, so step 1, done. Step 2, use unitary rates relating moles of one substance to moles of another. If it's 1 to 1? Oh, so this is just, yeah, we're just using, so kind of ignore the amount right now. Yeah, we're just looking at the balanced chemical equation. Yeah. All right, and then the question is how many moles? So now we can look at that number. How many moles of O2 equals 1 mole of magnesium oxide? Okay, so this part is maybe a little bit counterintuitive, or maybe it's not. I'm not sure. We'll find out. It does not matter if you are looking at things on the same side of the arrow or the opposite side of the arrow. We're just going to see a little bit of different wording, but we do the same thing. We use ratios. So I'm going to go 1 mole of MgO. And then my unit conversion rate is I've got 2 magnesium oxides for every 1 oxygen. So I've got to put my MgO on the bottom for every 1 oxygen. And what I end up with is 0.5 moles of O2. So I need 0.5 moles of O2. Yeah. Why did we take this? Why is this the ratio? Because in the balanced equation, there are 2 magnesium oxides for every 1 oxygen. So you use the balanced equation So to get the ratios, we use the balance equations. So if instead of asking, so if the question was how many moles of magnesium are required to react with oxygen, we would then use the ratio of 1 to 1 because we'd be doing magnesium oxide to magnesium. Does that answer your question? Or a little bit? Okay. Kind of think of this like a 2-part thing. So the first part of the question is just writing a balanced equation. So the first part of this is oxygen reacts with magnesium to produce magnesium oxide. So the first part of this question is just oxygen reacts with magnesium to make MgO. So we just write that out and balance it. So just like the last unit. And then the second part of the question is there's 1 mole of MgO. How many moles of O2 were needed? So just kind of think of it, like break it down into kind of 2 parts. Part 1 is just what we were doing in Unit 6, where we were taking things and writing balanced equations from word problems. And then Part 2 is actually taking the information about how many moles you need or how many moles you used. Does that make sense to you guys? Cool. All right. Let's decode the next one. I'll give you a second. We'll kind of decode the next one like that as well. Okay, so next question here is asking how many moles of hydrochloric acid are needed to react with 2.3 moles of zinc. So this is a 2-part thing. Part 1 is telling us the reaction. It's saying HCl reacts with zinc. Okay, so first step is we are going to write out a reaction. HCl plus Zn. What type of reaction is this? Singular replacement, yep. And what we're going to see is we got ZnCl plus H2. Balance that out. Right? Okay, so that's part 1. Does that make sense? Okay, and then the second part of this question is how many moles of HCl for 2.3 moles of zinc. So for that second part, we're going to need to use the ratio of zinc to hydrochloric acid that we found up here. What is the ratio of zinc to hydrochloric acid, you guys? Yeah, it's 1 to 1. Yeah. Oh, thank you. Uh-oh. Okay. I don't have any white out. Let's balance this. Oh. Right. It just needs a 2 here. Oh, there we go. That was very, very easy. Okay, thank you. Cool. So, change it. 2 hydrochloric acids to 1 zinc. Now it's 1 to 2. Okay, so the second part is how many moles of HCl for 2.3 moles of zinc. So we're going to start with what we know. There are 2.3 moles of zinc. Second thing we know is that for every 1 mole of zinc, there are 2 moles of HCl used. So for every 1 mole of zinc used in our reaction, 2 moles of hydrochloric acid are used. What we end up with is 4.6 moles of HCl are needed. Any questions about how I got from here to here? No, we're good? Okay, sweet. 137. I want you guys to try these for about 10 minutes, and then we're going to take a break, okay? So page 124, give those a go. Let me know if you have any questions. Does this feel all right so far? Wonderful. Okay. I hope that video wasn't too scary.